In addition to your regional climate, like for example, we're in the temperate climate, there are what are called microclimates, and micro means small. Microclimate means the climate of a small place. And the climate of a small place, a microclimate around one side of your house or another side of your house, can be different from the main climate that your house is in. And it can be caused by all kinds of factors, which we're going to look at one by one. Beginning with the sun. Solar radiation. Radiation, electromagnetic radiation, is emitted by all kinds of bodies in the universe, including stars like our sun. And this is a picture that shows, represents different wavelengths of radiation. So there's a certain wavelength in this part of the spectrum that happens to be light, and human eyes happen to be set up so they can perceive that wavelength, so that's visible light. But there are other wavelengths that are longer, so as we go towards the longer length of the spectrum, we get infrared waves. Those, as we'll talk about, those make you feel heat. And then even bigger waves are microwaves, like come out of your microwave oven or come out of the sky, and then beyond that, radio waves. We're going to focus on solar radiation in the infrared part of the spectrum. Solar radiation comes from the sun. Terrestrial radiation, in the same wavelength, comes from every object on Earth. So everything emits radiation. It emits more radiation if it's warm, less radiation if it's cold. And how this affects you as a designer is if you are in a room where you are getting more radiation than you give off, you're going to feel warmer. So for example, it might be a cold day, but you're in a room with a stove or a nice steam radiator on the wall. You're going to feel warm even if the air is cold. And if you're giving off more radiation than you get, you're going to feel colder. So here's a little bit of math as an example. Let's say we're walking around outside in October, so it's in the fall. It's a fall day. And your body, the human body, radiates terrestrial radiation at a rate of about 430 watts per square meter. That's us. So you're walking around outside and you go stand on some asphalt that's out in the sun. That asphalt is giving off radiation at a rate that's somewhere above 500 watts per square meter. Well, you only give off 430 watts per square meter. So you are giving off 70 watts less than the asphalt. The asphalt is giving off more. You're going to feel warm. Now you walk over to a concrete wall, and you remember putting your hand on concrete sometime in your life. It felt cool. So here you are, you're next to the wall, and it's in the shade, and that wall is still emitting radiation, terrestrial radiation. It's about 350 watts per square meter. But you emit 430 watts per square meter. You're emitting more than you're taking in, so you're losing radiation. You feel cooler. It turns out that the temperature of the air is just about the same wherever you go on a particular day. So you could be carrying a thermometer, let's say, at chest level and go walking around, and it's going to register about the same temperature everywhere you go. But what makes you feel warm or cool is not just the air, it's the terrestrial radiation. So if you stand next to some black asphalt, you'll absorb terrestrial radiation, you'll feel warm. If you go stand in the shade, you'll give off more than you're getting. You'll feel cool. And I just want to point out that there's a question in our assignment worksheet for today. I think it's question 2, and it asks you a question about this. So, when we're designing houses and we're thinking about solar radiation and terrestrial radiation, in the winter when it's cold here, we want to be able to absorb more radiation. So we want 2 things. We want solar radiation, radiation from the sun, coming in. So we'll have windows facing south that will let solar radiation in. And then we want some stuff in our room that will emit terrestrial radiation. So we want some kind of thermal mass in here. We want concrete, stone, that kind of thing. Then in the summer, we don't want solar radiation, so we're going to have overhangs and trees that will block that. The angle of the sun varies with the season, as you are aware. So here's a diagram of the Earth with its axis, which is tilted. And in the summer, we, in the northern hemisphere, are tilted toward the sun. We'll get more solar radiation and we'll feel warmer. Then we go on around to the winter. In the winter, we're still tilted, but now we're tilted away from the sun. We'll feel colder. And the sun angle also varies by latitude. That is, if you're at the equator, you're going to get a lot more solar radiation than if you're up here in the higher latitudes like Oregon, Washington, Canada. And in the summertime, here's a diagram of a house with sun coming in. In the summertime, the sun is more close to directly overhead, so you're going to get more radiation, but it's going to be concentrated over a small area, so it'll feel warm. In the wintertime, the sun is coming in at a lower angle. It's going to be spread over a larger area. Here's a diagram down here that shows us summertime, sun's rays coming straight down, and you can see the small area that's taking in that amount of radiation. Over here on the far right, in the wintertime, here are some sun's rays coming in at a low angle, same amount of radiation, but spread over a big old area, so it can't heat up as well. I want to mention a thing called the notebook test. If you have something that's dark, some dark object, if you have 3 of them that are identical, and if you have a black notebook, that works pretty well. 3 black notebooks, take them outside and put one of them down flat on the ground so that the sun's rays are going to be coming down nearly perpendicular to the notebook surface. Then tilt one so that it's nearly parallel with where the sun's rays are coming in, which will mimic what happens in the wintertime, but maybe stand your notebook up on edge. And then have a third notebook that's tilted kind of halfway, not down flat, not up vertical. And go off and leave those 3 notebooks for about an hour, then come back and put your hand on each one and see what you feel. And you are going to feel a hot notebook where the sun's rays were coming straight down, like they do in the summertime. We can figure out what angle the sun's rays are going to come in at a particular time of day and at a particular season of the year, and we are going to use something called a sun path diagram. This is an example. We're going to use a sun path diagram. We'll look at this next week, and we'll start to figure out how do you know what angle to set your house at and how long to make the overhangs over your windows. Another effect on microclimate is the slope of the land. So if you build a house on the south slope of some kind of hill, you are going to be getting some nice sunlight all year round. If you put your house on the north side of a slope, you are probably not going to be getting any sunlight. You'll be cool and shaded. Now, depending on where you are, what climate you're in, that might be good or bad, but you want to notice that it makes a difference. And finally, here's a big example of thermal mass. Large bodies of water like the ocean or big lakes, you can probably tell this is Lake Michigan, but other big lakes, those are thermal masses, which means they're a big chunk of material that heats up slowly and cools down slowly. So it takes them a long time to absorb heat in the summertime, and then it takes them a long time to release that heat in the wintertime. There's a big lag there. And what that means is that if you're next to a big body of water, whatever your climate would have been is more moderate because of this giant thermal mass you're next to. And here are some resources for you to read about microclimate.